Welcome back class to our course on mechanical behavior of materials part 2. So in the last lecture, we started talking about ascent curve, right? And we discussed that there are two types of curves we typically observe. I've shown here. You see, so one is for mild steel, BCC mild steel and titanium alloys, where we talk about finding endurance limit or fatigue limits, right? So the stress below which there is an infinite life. So that we discussed. Second is for aluminum alloy, magnesium alloy, etc., where there is no concept of endurance limit and the curve goes continuously down. Okay, so we talk about fatigue strength in this type of curve, where the stress corresponding to 10 to the power 7 cycle will be represented as fatigue strength of that particular material. Okay, so that is what we discussed, and then we also talked about how to represent it in terms of different R ratio and the effect of mean stress on the fatigue behavior, right? And I have shown here, so this is what we discussed in the last class, right? So if you increase the R ratio, the number of cycle to failure increases, right? So this is how your R ratio is increasing. And as far as the mean stress effect on fatigue behavior is concerned, so your mean stress, if you increase the mean stress, the number of cycles to failure will be decreasing. Okay, as shown in the second one. So this is what we discussed in the last class. Okay, so let's proceed further on the same topic. So, when we talk about the effect of mean stress on the fatigue life, many empirical relations have been proposed. Okay, so let's talk about that first. So various empirical relationships have been proposed. Okay, for effect of mean stress on fatigue life. Okay, so we will talk about Goodman, then Soderbergh and Gerber. Okay, so these three are empirical relationships. Okay, and these are scientists' name who provided these empirical relationship, and they discuss about the effect of mean stress on the fatigue life. Okay, so let's talk about first Goodman relationship. Okay, so here what we are doing, we'll plot of sigma mean and sigma max versus sigma m. Okay, and when we talk about sigma mean and sigma max, we can plot also sigma a, right? The amplitude, stress amplitude. Okay, so let me plot that. Okay, so So this is sigma E minus sigma E. Okay. And here we are plotting stress on the y-axis and sigma m on the x-axis. Okay. So this line will correspond to sigma max. This line will correspond to sigma minimum. Okay, and then this particular point is UTS. And somewhere here say you have yield point Y. Okay. Okay. So this sigma E, this is endurance limit, right? Or fatigue limit. Okay. So cycling between the region, right? So we have plotted sigma max and sigma mean, and remember this is valid for either the fatigue limit or certain number of cycles. So valid for a particular number of cycles or fatigue limit. Okay, so what we are in fact doing, if you remember, we discussed this. So we have different sigma m, right? So say this is sigma 1, sigma m1, sigma m2, sigma m3, sigma m4, right? Sigma a here. So sigma a we can write in terms of sigma minimum and sigma maximum. And then here you have nh. So if I take say particular n value, right? For different sigma m, so if I take sigma m1, for this particular nf, we know what is sigma a, right? So that is what we are plotting. So either a particular number of cycle or we just take the endurance limit, okay, for each sigma m. So that is what we are plotting here. So for each sigma m, we are going to get different sigma maximum and sigma minimum, right? So say for this particular value, you are going to have different sigma maximum. So this is sigma maximum and this is sigma minimum. So for different sigma maximum, sigma mean that is average, we are plotting sigma maximum and sigma minimum, something like this. And what you end up getting is your red curve. Okay. And when mean stress is 0, that is R equal to -1, that becomes endurance limit. Okay. Now, if we are in this particular regime, in between this, if we cycle it, you are not going to have fatigue failure. So this is a safe region. So no fatigue failure. Okay. So that is one point. And if you are above sigma max line and below sigma mean line, then there will be fatigue failure. Okay. So using this diagram, you should be able to know what is the range of sigma max and sigma mean we can take so that the fatigue failure doesn't occur for that particular specimen. Okay. Second, if you increase the mean stress, what you are observing that sigma A continuously goes down and finally it reaches to a value of UTS. So uniaxial tension. Okay. So you can see here. So if you increase sigma mean m sigma m, right? This goes down, right? So sigma maximum and difference between sigma maximum and sigma minimum is going down. So sigma amplitude, right, or stress amplitude goes down. And finally, it reaches to value of UTS here, which is uniaxial tension or tensile strength in uniaxial tension. Okay. So if I just write down the relationship, it will be sigma A equal to sigma E 1 minus sigma M by UTS. Okay, where sigma A, you know, its stress amplitude. Sigma is your endurance limit. Sigma M is your mean stress and UTS is tensile strength in uniaxial tension. Okay, now if sigma M goes to UTS, what happens to sigma A? If you see the right diagram, sigma max becomes equal to sigma mean, right? At this particular point here on the left diagram, sorry, right? So sigma A is equal to 0. So it is satisfying, right? Okay. Similarly, if sigma M tends to 0, right? So I'm talking about now this particular point. What happens to sigma A? Sigma E. You can see here, right? So you are having sigma E. This sigma A. This becomes equal to sigma E. Right? So this particular equation here nicely, you know, satisfy the plot I have shown here. Okay. Now what Soderbergh proposed is more conservative criteria. So instead of UTS, Soderbergh proposed that we can use yield point, yield stress, right? So the equation now will be sigma A, sigma E, 1 minus sigma M by YS. Okay, where YS is your yield strength. So that is what proposed by Soderbergh. And the last one is Gerber. So Gerber proposed the least conservative out of these three, huh? Relationship, and that goes as sigma A, sigma E, 1 minus sigma M divided by UTS whole square. And now if I plot all three in stress amplitude versus sigma N plot, so we are plotting sigma A versus sigma M. Okay. So if you see Soderbergh and Goodman, so let me write down Goodman again here. So it is sigma A, sigma E, 1 minus sigma M divided by UTS. So both Soderbergh and Goodman relationship in straight line, right? If I plot sigma A versus sigma M, right? Y equal to S plus C. So here if I, let me plot first Goodman. Okay. So this will be UTS, right? So if I place here sigma A is equal to 0, sigma M will be UTS. Okay. And similarly, if I place sigma M equal to 0, sigma A will be sigma E. So this becomes sigma E. Right? That is for Goodman. Now let me draw for Soderbergh. So Soderbergh says if I now use this equation, sigma A is equal to 0, then sigma M will be YS. And YS is less than UTS. So say YS is somewhere here. Okay. Similarly, if sigma M is equal to 0, sigma A is equal to sigma E. So this condition is similar to what we observed in Goodman. So this point remains same in both the cases. So, and this is a straight line. So it will be something like this. Okay, both are a straight line. So this is for Soderbergh, and this red line is for Goodman. Okay, now the last one is Gerber. So it is sigma m square, right? So it is going to be something like this. Okay, so out of these three, if you see, Gerber is the least conservative and the Soderbergh is the highest conservative out of these three we are talking about, right? So if you are in the region below Gerber, right, then the sample is not going to fail. So you have to be below these three curves for respective relationship to be valid. And if you are above the curve, your sample is going to fail. Okay, so this is how you can represent stress variables using Goodman, Soderbergh, and Gerber relationships. Okay, so now let's move to high cycle fatigue and low cycle fatigue. Right. So in the last lecture, I described about high cycle fatigue and low cycle fatigue. I told that around 10 to power 4 cycle, if it is below than that, then it is low cycle fatigue. If it is higher than that, then it is high cycle fatigue. Right. And the SN curve, what we discussed till now, is based on the strains controlled experiment, right? So we are varying stress and then we are plotting SN curve. Okay. So in high cycle fatigue, stress values are typically low. Okay. This means that the nominal strains, we can assume that nominal strains are going to be elastic because stress values are low in high cycle fatigue. Okay, and if that happens, we can nicely apply Basquin relationship. Okay, and what is Basquin relationship? It is in terms of sigma A, sigma f dash to nf to the power b. Okay, now sigma A can be written as delta sigma by 2, right? You remember? So delta sigma is this, and sigma A is, if this is your mean stress, then sigma A is delta sigma by 2. So this is sigma A, right? So sigma A is delta sigma by 2. So we can write now delta sigma by 2. So delta sigma we can write in terms of elastic strain and Young's modulus. So that will be, okay, where delta epsilon is elastic strain range, right? And E is your Young's modulus. Okay, now we can write delta epsilon E by 2 as delta sigma by E. Okay, not delta sigma, sorry, sigma A by E. So I'm just bringing this E here. Okay, so delta epsilon E by 2 will be sigma A by E, and sigma A we know, if I write this as equation 1, So if you use equation 1, it will be sigma F dash by E to NFB from equation 1. Okay. So overall, the Baskin relationship is given by delta epsilon E by 2 to NF by B. Okay, and this is for high cycle fatigue. What is NF? So NF is your number of cycle to failure. Here instead of NF, what we are using is 2NF, right? And 2NF is number of reversals to failure. Okay, so number of reversals. So in one cycle, you have two reversals, right? So if NF cycle is number of cycle to failure, then you have to multiply it by 2 so that it will be total number of reversals to failure. Okay. Sigma epsilon E by 2 is your strain amplitude, or in this case, elastic strain amplitude. Okay, remember we are using elastic strain here because the nominal strains in high cycle fatigue is elastic. We are assuming that stress values are very, very low. That is what I have written here. Okay, so we can nicely use the stress, Young's modulus and strain relationship. That is what we have done. Okay, what is sigma F dash? This is called fatigue strength coefficient. And this is equal to stress intercept at 2NF equal to 1. Okay, now what is left? B. So B is fatigue strength exponent. Okay, so I have defined all the terms here in Baskin relationship. Now let's take log in both the side, on both the sides. So you have so this is the relationship. Now we are taking ln. So if we plot log of delta E by 2 versus log of 2NF, it is going to be straight line with a slope, right? And that slope is B. You can measure B. Okay, and the intercept, if you take, that will be ln sigma F dash by E. You know what is the E because you know the material, can calculate what is sigma F dash. Okay, so you can actually know what is the Baskin relationship after you know what is B and what is sigma F dash. Okay, so this is for high cycle fatigue, right? And this is stress controlled experiment, right? You know, in many scenarios, you are going to observe strain controlled conditions, especially when we talk about thermal fatigue. The material will be subjected to, the component will be subjected to constant strain, right? So it is also important to understand the constant strain controlled experiments, or and you know that will be typically used when we talk about low cycle fatigue. Okay, so strain controlled experiment. and we talk about this typically in low cycle fatigue. Okay. So when we have low cycle fatigue, so now what is the number of cycle? It is less than 10 to power 4. Right? Typically tests are conducted in strain control mode. Okay. So instead of stress control, we are controlling now strain. We are maintaining strain to be say constant, and then we can do constant strain amplitude test. Okay. And since we are talking about low cycle fatigue, the stress, corresponding stress is going to be higher. That means the strain is nominal strain is plastic. Okay. Why? Because stress is higher. Huh? We are talking about low cycle fatigue, so stress is higher. So for relatively low value of n, the plastic strain is much greater than the elastic strain. Okay, so if our value of n, right, number to failure, say it's very low, right? For all practical purpose, we can assume that the plastic strain associated with it is going to be much higher than the elastic strain, right? Because the number of cycle is very low, that means our stress value is also very high. Okay, so we can assume that E total is E plastic, so where EP is your plastic strain. So we are assuming EP is greater than E. Or since this is fatigue, we can say, delta E. Say something like this. Okay. So here the relationship, can be, so there is an empirical relationship for low cycle fatigue that is given by Coffin-Manson relationship. And it is given as delta EP by 2. So we are neglecting elastic strain. Okay, assuming that the number of cycles is very low. So the elastic strain is low compared to the plastic strain, and something like this. Okay, so this is Coffin-Manson relationship where C is your slope after you take ln. So let's take ln on both sides. So if I take ln, your equation will be okay. So C is your slope of plot of ln delta EP by 2 versus ln 2NF. Okay. Delta EP by 2 is plastic strain amplitude. NF, we know its number of cycles to failure. Now we are talking about 2NF. That also we know it is number of reversals to failure. Okay. Then what is eta dash F or eta F dash? That this is called ductility coefficient in fatigue. and this is equal to strain intercept at 2NF equal to 1. Okay, and see the slope. This is called ductility exponent. In fatigue. Okay, so we have discussed about high cycle fatigue where we can use the Baskin relationship, and in low cycle fatigue we can use Coffin-Manson relationship. So both are opposite to each other, right? One is where we have predominantly plastic regime and strains are plastic, and in another one strains are elastic in nature. Okay, so overall, if I say the total strain can be superimposition of both plastic strain and elastic strain, isn't it? So we can write for a material subjected to a total strain range of say delta epsilon t, okay, which has both elastic and plastic strain. Now these both can be superimposed. So we can write delta epsilon t by 2 is equal to plus plastic part. Okay. Now delta epsilon E by 2 is Baskin relationship. So that is given by this 2NFB, and then delta epsilon P by 2 will be from Coffin-Manson relationship, and this will be given by this. Okay. So now we know what is the total strain amplitude. Okay, that is a combination of both Baskin relationship and Coffin-Manson relationship. Okay, and remember the Coffin-Manson relationship is for low cycle fatigue and the another one is for high cycle fatigue. Okay, so now it is expected. So now we expect that the curve of fatigue life, right, in terms of total strain, it will tend to plastic curve when, or say Coffin-Manson relationship when we have very large strain, and when the strain is small, it will tend to merge with the Baskin relationship or the elastic curve. Okay. So curve of fatigue life in terms of total strain will tend to plastic curve. I will draw a schematic for better understanding. So this will be Coffin-Manson. Okay. And this is going to happen at large total strain amplitude. Okay. And if the total amplitude or total strain amplitude is small, what will happen? The curve of fatigue life will tend toward elastic curve, which is basking. Okay, so now let me draw what I'm trying to explain here. So we have 2NF and it is in log scale. Here you have delta epsilon by 2 again in log scale. Okay, so my curve is say something like this. Something like this, okay, approximately. So for basking, we can have a plot okay, and for Coffin-Manson, you are going to have another plot. Something like this. Rough schematic. Okay. So this is for plastic. I will show you schematic later on. Good schematic. Okay. So this is for plastic Coffin Mansion. Okay. And then we have the blue one for basking. Is elastic. Okay. And the red one is my curve, right? Say fatigue life curve. So what you see here that at very large strain, it is tending towards the Coffin-Manson plot, which is here, okay, at very large strain values. So it is merging towards the plastic curve, right? And at very lowest strain, it is merging towards the Baskin relationship, which is here. Okay. So when your total strain is low, we can nicely use the Baskin relationship as I've shown here. And when your total strain is high, you can nicely use the Coffin-Manson relationship. Okay, that is what it is shown here. And remember, both Coffin-Manson and Baskin both are straight line. I have just drawn the schematic. It doesn't look very nice, but I will show you eventually a nice schematic. I will draw it and then I will show you in some class later on. Okay, so this is what I wanted to discuss about ascent curve, high cycle and low cycle fatigue. In the next lecture, we'll start talking about the process of fatigue damage. Okay, so we'll start talking about the initiation and propagation mechanism when a sample is subjected to fatigue loading. Okay, thank you.